I'm going to talk about international climate policy, and I'm going to do so in 4 chapters. I'm going to talk about international cooperation and free riding. I'm going to talk about cartel formation. And then in the second half, I'm going to leave game theory and talk about first what happened during the international climate negotiations. And then I'm going to talk about 2 international success stories, acid rain and the hole in the ozone layer. Tell you why they were successful, but also tell you why these lessons, these successes do not apply to climate policy, why the 2 problems, the 3 problems, are structurally different. This is the last in the series on climate economics. We started with talking about emissions and emission reduction. Then we talked about the impacts of climate change and why we think it is a problem. And then 2 weeks ago, I brought the costs of greenhouse gas emission reduction and the impacts of climate change together in the cost-benefit analysis. Last week, we talked about the definition of optimality. But over the last 2 weeks, I assumed that there was a single global social planner. And this week we're going to abandon that particular assumption and look instead at what happens if there's multiple national social planners. And I'm going to do so starting with international cooperation and free riding using game theory. When we talked about optimal climate policy, essentially what we argued is that if you want to find an optimal course of action, then what you do is you equate the marginal costs of emission reduction to the marginal benefits, the avoided impacts of climate change. And we said, well, one is a stock, the other is a flow, so really what matters is the net present value of those benefits. But essentially what you do is you equate marginal costs to the marginal benefits, and what you find almost always is that this is an interior solution. You neither go for no emission reduction whatsoever, nor would you go for 100% emission reduction. We talked about the supply curve, the marginal costs of greenhouse gas emission reduction, or the carbon tax that you want to impose, the permit price that you want to tolerate, and that is shown in this graph. And the harder you work, the more it costs. The key thing here is that the costs of greenhouse gas emission reduction are largely determined by what is going on in your own country. It's essentially determined by how hard you work on emission reduction. There are some spillovers across international borders. They have to do with international trade, has to do with international investment, and on a longer time scale, research and development into alternatives to fossil fuels. But by and large, how much it costs depends on how hard you work on reducing your emissions rather than on what other countries do. So this particular curve is not just valid for the world as a whole, but it's also valid for every particular country. These are the marginal benefits of greenhouse gas emission reduction, and these do depend on what you assume is going on outside your borders, because what you're looking at is estimates of the global social cost of carbon, or if you evaluate it along an optimal trajectory, the global PDU tax. Because CO2 mixes uniformly in the atmosphere, the concentration of CO2 is shared between all countries, and therefore its effect on climate is shared between all countries. That means that your climate is determined not just by your emissions, but also by the emissions of everybody else, but vice versa. The benefits of your emission reduction are not just in your country, but are spread across the world as well. And that means that most of the benefits of what you do to reduce emissions will fall outside your borders. And in a global optimum, that doesn't matter because they don't spill to Mars or Venus. But in a national optimum, what you do in the UK with emission reductions does spill to Bangladesh and Ghana and the United States. And that is the crucial thing to remember, and that explains what is going on here. What you're looking at is a graph from a 1996 paper in the American Economic Review by Bill Nordhaus to your left and Zili Yang to your right. And what you're looking at is not emissions and not temperature, but rather the concentrations of carbon dioxide in the atmosphere, or even better, the load of CO2 in the atmosphere. And this is depicted over the 21st century. There's 4 lines on the graph. In the very top, you're looking at a situation with hardly any climate policy, denoted the market solution. Very bottom, you're looking at a previous version of this model. This is the RISE model of 1996, and what depicted here is the DICE model of 1991. It's just a different calibration, and they put it in for comparison, not because it is insightful in any way. What matters are the 2 lines, cooperative optimum, called equilibrium here, and the non-cooperative equilibrium. In the cooperative optimum, what you do is you set the regional marginal costs of emission reduction equal to the global social cost of carbon. And what you see is what we saw before. You see a little bit of emission reduction, not nearly enough to stabilize, but you see action. In the non-cooperative equilibrium, the regional marginal cost of greenhouse gas emission reduction are set equal to the regional social cost of carbon. And what you see is much less emission reduction and much higher concentrations of CO2 in the atmosphere. And the reason, the intuition for this is quite simple. What you're looking at here is a picture not of this from this particular paper, but a much later iteration of the same point. What you're looking at are the top 25 or so countries measured by their national costs of emissions at the margin. The global total in this particular scenario, in this particular model, is $24 per ton of carbon, and what you see displayed here are the national costs of carbon. The key thing here is the horizontal axis, which runs from 0 to 7. Global total is 24, but the scale here runs only to 7. And if you look at the country with the largest marginal costs of emissions, it's India, and that number is 5.5. Now, why does India come on top? This is an absolute measure. So if you have a larger economy, if you have more people, then you're going to suffer more damages in absolute terms. India is a big country, and we also said that poorer countries are more vulnerable to climate change. And so a country that is big and poor, India, comes out on top. Ethiopia comes 3rd, and Bangladesh comes 4th, and Pakistan comes 5th, right? These are very big and fairly poor countries. And China is just very big, but fortunately not nearly as poor as it used to be. But the key thing here is that even the biggest national contribution to the global social cost of carbon is only a fraction of the globe, right? So India is 5.5 or so out of 24, so let's make that a quarter, right? And all other countries are small, and if you look at the 25th country on the list, that's Mexico, the national cost of carbon at the margin is only, what is it, 15 cents per ton of carbon. So if Mexico disregards the impacts of its emissions outside its borders, it would apply a carbon tax of 15 cents on its emissions rather than 24 cents. And that explains why the non-cooperative equilibrium is so much closer to doing nothing about climate change than the cooperative optimum. It's as simple as that. So, in words, if we assume that the national cost of greenhouse gas emission reduction are primarily determined by the national emission reduction effort, which is a reasonable assumption, it's not 100% accurate, but it's a reasonable assumption, then in the cooperative optimum, you essentially said the national marginal cost of emission reduction equal to the global marginal benefits, whereas in the non-cooperative equilibrium, you said the national marginal cost of emission reduction equal to the national marginal benefit. And that immediately explains why cooperative action is so much more ambitious, because the global marginal benefits are necessarily larger than the national marginal benefits, because the globe is the sum of the nations. So the next question is, can cooperation be sustained? And in order to answer that question, I'm going to use a LQ game. I'm going to assume that the costs of greenhouse gas emission reduction C is a quadratic function of the effort, the relative effort R, and I raise that to the power 2 and multiply it with a parameter alpha. So these are the costs of emission reduction. This is a quadratic equation, and that's the Q in the LQ game. The benefits of emission reduction, B to country I, depends on how sensitive it is to the impacts of climate change, beta, and it depends on not just what happens in country I, but what happens with emission reduction in the sum total of all countries in the world. So we sum over the countries J, R with relative, so we need to multiply it with emissions E. And this is a linear equation, and this stands for the L in the LQ game. So it's a linear quadratic game. The good thing about linear quadratic games is that if your objective function is at most quadratic, then your first order conditions are linear, and that means that you know there is a solution, because we can solve a system of linear equations, no problem. And that's the only real virtue of an LQ game. It has an analytical solution. In the non-cooperative equilibrium, what you do is you set the marginal cost of emission reduction, BCDR, equal to the marginal benefits of emission reduction, BDR. BCDR is simple, 2 alpha R squared becomes 2 alpha R. The benefits of emission reduction, you need to work out the sum, but realize that for that drj dri is 0 unless j equals I, so only beta I and EI remain. So this is your first order condition, and this solves as R asterisk is beta I EI over 2 alpha I, and this is true for all countries I. The cooperative solution, essentially you're interested in the sum total of emission reduction costs and the sum total of benefits of emission reduction. Now, as I said, the assumption is that there's no spillover between countries in their cost, so this just stays the CDR is 2 alpha R, 2 alpha I RI. What you're interested now is, what do your emissions RI do to not just the benefits in your country, but the benefits in all countries. So you need to sum over all countries J the benefits. Now, this does not depend on the RJs, it only depends on the RIs. So what matters is your contribution to the problem, your emissions. And now you're not only interested in what your emissions do to yourself, EI beta I, but you're also interested in what your emissions, EI, do to the impact in your neighboring countries, and that is beta I plus beta j for all j's that are not I. So we now have this summation here, and our prime, the optimal emission reduction, is beta times EI over 2 alpha I. So that is the difference between the cooperative and non-cooperative solution. Now that's not what I'm interested in. I'm interested in free riding. Now what is free riding? Free riding is a peculiar concept. The starting point of an analysis of free riding is that every country collaborates with one another. The starting point is global collaboration, global cooperation. And then a particular country, I, wonders what happens if I stop collaborating, if I stop working with the others, if I stop playing nice, assuming that all others continue to collaborate. And that is essentially what free riding is about. This is something called Nash behavior, which is a misnomer because John Nash had nothing to do with this. He was much smarter than that. But this is the basic assumption in free riding. What happens if I stop playing nice, assuming that all others will continue to play nice? Okay. If you're considering to not play nice, why would you think that others would continue to do so? So that is the peculiar assumption in free riding. For this consideration, there's costs and there's benefits, right? So the difference in costs, if all others continue to collaborate, but you stop collaborating, the difference in costs is C prime minus C asterisk, C prime minus C asterisk. Because we assume that the costs of emission reduction only depend to a particular country, only depend on what is happening in that particular country, this is simply C prime minus C asterisk. So that's, you plug in the R's that you have in your cost function, so that's beta squared EI squared over 4 alpha I. Same for the non-cooperative solution, and the E's and the 4's and the alphas stay the same, so this is beta squared minus beta I squared. The difference in benefits depends much more crucially on the definition of free riding, because the assumption is that all others maintain their collaborative behavior. So their emission reduction efforts do not change. It's only your emission reduction effort that changes. So it's not the cooperative solution minus the non-cooperative solution. It's not B prime minus B asterisk. It's B prime minus B double prime. And the only thing that changes is your behavior. So it's your contribution to the problem, your emissions times your vulnerability, because you only care about yourself. And then only you are changing in behavior, so the summation sign is not there, and we have R prime minus R I asterisk. Plug the R's in again, and what you have is that the difference in benefits, if free riding, is beta I times beta minus beta I times E I squared over 2 alpha, right? So if we compare these two equations, the EI squared is there in both situations. So if we compare the two, that essentially drops out. The same is true for the alpha. Here we have a 4, here we have a 2. So essentially this is half the size of this. And then the other difference is that here we have a BI squared, but here we also have a BI squared. Here we have a beta squared, but here we have a beta times a beta I. And we have thus proven that it's always optimal. It's always in your own self-interest to free ride. Now, if that went a bit too quickly, let's plug in some numbers. So the equations that you see are the same as the equations you saw before. with some of the intermediate terms cut out, but the result is exactly the same. As I said, E doesn't really matter, so let's set that equal to 1. Alpha doesn't really matter, it's multiplied by 2, so let's set that equal to 1/2, just to make the calculations a bit simpler. And let's start with the situation of India, where the national social cost of carbon is a quarter of the global social cost of carbon. So set this arbitrarily equal to 1, and this one arbitrarily equal to 4 times the size, that is 4. Now if you plug in these numbers into these equations, what we see is beta squared minus beta I squared is 4 squared 16 minus 1 squared is 1 is 15 divided by 2. Alpha is 1/2. That makes 7.5, right? Difference in benefits, 4 minus 1 times 1 is 3, times 1 is 3. So should a country the size of India that covers a quarter of all benefits decide to leave the global coalition, then it would gain 7.5, it would avoid costs of 7.5, and it would suffer additional impacts of climate change of 3. Now 7.5 is greater than 3, so essentially it gains 4.5. This is a good deal for a country the size of India that makes up a quarter of the globe and measured in marginal benefits. What happens if we make the country smaller? That's not what I do. I make the globe bigger, and now the country suffers at the margin 10% of the global impacts, right? So what happened to the costs? It's 10 squared minus 1 squared over 2. That's 99 over 2 is 49.5. Difference in benefits is 10 minus 1 times 1 is 9. And this number, it's still, the change in cost is much larger than the change in benefits, so it makes sense to leave the global coalition. It makes sense to free ride. And this number is much larger relative to this number than this number is relative to this number, right? So smaller countries have a relatively greater incentive to leave the global coalition. So obviously I changed the numbers in the wrong direction, so let's now make the globe smaller, and we assume that beta I is 1/2 of the beta, so this is 2 squared minus 1 over 2 is 1.5. 2 minus 1 is 1. So even if you as a country are 1/2 of the marginal impact of climate change, then still it makes sense to not collaborate with the others. And half of your problem is still determined by what is going on in the rest of the world, and you're still not interested in international collaboration. Now this is true for the 3 sample countries that we're looking at here. It's true for every sample country with reasonable numbers that you plug in. And that is why the cooperative solution that Nordhaus and Yang called an equilibrium is not an equilibrium. It's in everybody's interest to run away from, to free ride on the global coalition. And therefore that global cooperation would collapse. It's not an equilibrium at all. And the realistic scenario is a non-cooperative one that is here called an equilibrium because it is an equilibrium. That is the sorry state of affairs. Greenhouse gas emission reduction is essentially a global public good, and without an international authority to enforce the provision of a global public good, the bunch of sovereign countries, you will not get there.